Hello, my name is Eric Subchak, and today I wanted to talk to you about mass spring systems and how we can use differential equations to model their position over time. Let's start by modeling an equation for mass spring systems. As with most things based in the real world, we can model their movement using Newton's second law. Because we're interested in the position and not acceleration, we can change the a to a y double prime to indicate the second derivative of position, which is acceleration. We are going to assume the spring we are modeling is an ideal one. Because of this, we can use Hooke's laws to model its return force back to its equilibrium point. We also want to take into consideration any sort of damping force that might be acting on the mass, and this can be modeled using By prime, where y prime is the velocity of the spring. Lastly, we need to consider any sort of external force that might be acting on the system. This is usually a function of time and can be written as f of t. Now we can go ahead and rewrite our equation, and we have the basis for any mass spring system problem. Let's start small and begin our focus by looking at a problem that's undamped and has no external forces. Consider a mass spring system where a mass of 1/4 kilogram is in an ideal spring with spring constant 16 Newton meters. Find the solution if the mass is released 1 meter below equilibrium with no initial velocity. We can pull the constants out of this word problem and plug them into our mass spring system equation. Now we can just solve it like any other second order differential equations. Because it's equal to 0, we just need to worry about the homogeneous equation. We can rewrite this entire equation as a quadratic and solve for the roots. Based off the type of quadratic, we can put the roots into one of 3 general solutions. Because the roots here are plus or minus 8i, we can use the general solution for complex roots. We can now use our initial conditions to solve for c1 and c2, and we're left with the final equation, y equals cosine 8t. This equation models the mass over time, and when we graph it, we can see that it oscillates indefinitely. This makes sense as there's no damping forces to slow it down. Now once we start adding a damping force, 3 different scenarios can occur. Because we would still be using the quadratic root method to solve, we can analyze the result of the root to predict how the function will behave. If all the roots are distinct, the resulting motion will be overdamped and no oscillation will occur. The function will go straight to equilibrium. If the root is repeated, the resulting function might overshoot equilibrium slightly, but will still avoid oscillation and go towards equilibrium. This is known as critically damped. The final possibility is if the roots are complex. This will result in underdamped motion, where this oscillation force is stronger than the damping force. Some oscillation will occur, but the function will still move towards equilibrium. Now, instead of a damping force, let's look at an exterior force. These are your scientists with sticks poking around at the system. An interesting case is when the exterior force matches the frequency of the oscillation of the system. In this case here, the 2 cosine t matches the oscillation pattern of the y double prime plus y. We can solve this differential equation using similar methods to the ones above, but we must also consider the y particular solution. We can find it using Mach and add it to the homogeneous solution. Apply initial conditions, and we're left with y equals t sine t. A lot of numbers for such a small equations. When graphed, you can see the resulting oscillation continues to amplify as time goes on. This is called resonance, and it's the same thing that causes those wavy bridges. If the exterior force is offset by a slight amount, the resonance effect will no longer occur as the 2 frequencies are no longer in sync. To model this, let's make a slight change in our equation and multiply the t by 0.9. We can now see that the resulting graph is very different. The oscillation no longer amplifies, but the 2 interfering frequencies do create an effect called beats. The 2 cosines fight with each other to create this interesting line. We can see that with some math, we can use differential equations to model the real world.